Okay, I think it's time to start. Welcome to this afternoon session. It's my great pleasure to introduce Panos Kevrekidis from UMass, University of Massachusetts. And Panos will talk about dark solitons from 1D, 2D, 3D, and some quantum touche.
Let's see. All right, thanks very much to Ionut. Thanks to all the organizers for having me here. And thank you all for coming after lunch. I hope I won't put you to sleep. Let's see. So this is work with a number of good friends and collaborators. As I usually say, whatever good you see in here should be attributed to them. Whatever bad should be blamed on me. We've done a number of things over the years. I'll be happy to give specific references to anyone that is interested. But here's what I really want to tell you about today. So I don't think I need to sort of preach to the choir to tell you about what BECs are, but I'm just going to refer to what equations I'm going to be using. I want to really kind of take you through a path of experiments in repulsive atomic BECs. And one of the things that I think is interesting in this community is to tell you a little bit about analogs to these. And I know some of the people like Nick Prokakis have been doing this as well. Analogs with nonlinear optics, because I think there are interesting parallels and analogs to draw between the two areas. I want to really kind of go a little bit into the mathematical tools that I'm going to be using, something about the near linear limit and highly nonlinear limit. So here there are going to be some mathematical methods. And then there are going to be some extensions to multi-component systems and multi-dimensional systems. And then maybe mention a little bit towards the end something very recent rather than the quantum touches, something about peregrine solitons that you may not have heard before. Okay, so this I'm going to skip as well as this one. Here's kind of the lay of the land. Okay, so I'm going to be thinking about Bose-Einstein condensates, so thinking about sort of low densities, low temperatures, such that the GPE is a good description. So here's the GPE. I think it wasn't perhaps shown before. Here it is in its full three-dimensional glory, and with external potentials. And so I have to tell you something about what the external potentials describing this low density, low temperature, but high atom number BECs. So I'm going to be thinking mostly or much about one-dimensional condensates, so elongated traps. And in these elongated traps, I'm going to be thinking mostly about parabolic potentials, parabolic confinements. I will do something about 2D, and there I will also have either parabolic or periodic confinements, and then I'll go also in 3D. And most of what I'm going to be telling you about has to do with the fact that in 1D, there is some stuff that we know and love about this equation. This equation in 1D without any potential is actually integrable. That is, for the students, you give me initial data, I can propagate them in time for all time. And so one of the things that we know about the equation is that it has explicit solutions. If the interactions are repulsive, if the medium is defocusing, as we say, we know that there is an exact solution in the form of a dark soliton. What's a dark soliton? A dark soliton is a state in which atoms are on the left, atoms are on the right, and then there is a density dip in the middle. Okay, so there's an atomic dip, if you will, and it's mathematically described by this formula. So that's kind of going to be the protagonist, if you will, of much of my story. I did mention about multiple components. In multiple components, I'm thinking of multiple hyperfine states of the same gas, like rubidium-87, for example, or sodium, and then equations that have multiple components are coming into play. Okay, so I want to look a little bit at those as well. And so here's kind of my starting point of my story. This is 1999, shortly after BECs were realized in the lab, and people realized that, oh, this equation in 1D is something, has these kinds of solitons, has these kinds of structures. So let's look for them in experiments. And so this is NIST at the time, 1999, Bill Phillips's lab, where they were trying to do experiments in which there were atoms on the top, atoms on the bottom, and a density dip in the middle, sort of like the tanches that I mentioned before. Okay? I'm also showing you these experiments to get a sense of the spatial and temporal scale of these experiments. About 100 microns across. The experiments lasted only a few milliseconds. I'll explain why in just a second. And these experiments initialized something that looked like a tangent along this vertical direction. But notice, it is not really a one-dimensional state, right? It looks really like a two-dimensional filament, I will call them, line of a soliton, rather than a point soliton. In fact, it's worse than that. It's a three-dimensional condensate that has been projected on a two-dimensional plane. Okay, so this is really not a one-dimensional structure. And that has a bearing in the dynamics, because over time, these dynamics start bending, and eventually they break. they break to the canonical patterns that emerge in higher dimensions, the ones that Carlo told us about, vortices and vortex rings. So these solitons turned out to be very quickly unstable in these experiments because of this curvature-driven dynamics. We'll come back to that in a little bit, okay? So these experiments lasted very little. The solitons were not very robust, and that's something that we would like to understand. At around the same time, the group of Klaus Sengstock in Hanover was doing similar experiments in which thermal effects were quite significant. And dark solitons, these kinds of states, were also disappearing very quickly in those experiments as well. So these are experiments of the late 90s that had this kind of fate. Now I'm going to sort of march forward by about 10 years and going to tell you much more one-dimensional experiments. These are happening in the group of Markus Oberthaler in Heidelberg, and they are experiments in which actually what they were doing is they were kind of taking two atomic blobs and they were making them interfere. When you have atoms that interfere, they form interference fringes. Interference fringes in the presence of nonlinearity form these kinds of dark solitons. And these dark solitons will now propagate very robustly. They will oscillate and interact again and again over very long, much, much longer noticed timescales than the early ones, about 70 milliseconds, and these guys are still there. Okay? Now you might say, oh, this is not that impressive. This is just a single experiment, perhaps. Actually, those of you that know quite well this field know that imaging is destructive in most cases. So these are not a single experiment. Every pixel is a separate experiment. Okay? And in fact, it's even worse than that. Every pixel is about 10 experiments that are averaged out. This is done to illustrate that the quantum fluctuations, the thermal fluctuations and everything of that sort does not disturb the deterministic Gross-Pitaevsky-driven picture that we talked about before. So this averaging tells you that very robustly these things keep reproducing, keep oscillating, keep interacting for these very long times. In fact, single-shot experiments can go to seconds without variation. Okay, so they will be very long-lived. And so this reproduces very well the GPE. And speaking of the GPE, here is the GPE result corresponding to this experimental realization. And you might think, well, this doesn't really correspond to that exactly. Well, if you convolve it with the experimental resolution, you get this picture. So this is kind of the picture that you need to compare with that experiment. So the picture clearly reproduces these oscillating and interacting dark solitons for these early experiments of Markus Oberthaler, or these 2007 experiments of Markus Oberthaler. And if you understand something about integrable theory, you understand also how to create more solitons than just two. For example, if you have two atomic blobs, if you have them in phase, you will create an even number of solitons. But if you have them out of phase, by construction, you will generate a soliton right in the middle. You will generate a soliton at the middle that will persist forever after. So this gives you a way to actually produce odd numbers of solitons. And in fact, if you know your integrable theory, you also would know that if you separate these atomic blobs more and you allow them to interfere, you will produce more dark solitons because the dark solitons seek to fill the empty space between the atomic blobs. So if you separate them more, you can generate 4 solitons instead of 2, or 5, or 6. So you see, this is kind of a playground of generating as many solitons as your heart desires. So you can do 2, 3, 4, and so on and so forth. So these were the experiments of Markus Oberthaler's group in Heidelberg, but around the same time there was a big activity along this direction. A little bit before that were these experiments by Peter Engel's group in Pullman at Washington State, where Peter was taking a dipole beam, was sort of taking it, sweeping it through the condensate, and was observing the result of the evolution. And during this result, he was seeing structures like the ones we talked about before, like this one, that looks like a dark soliton. But look at this, it also had structures that looked like fragmented dark solitons. And we'll see that these were not quite dark solitons, but other kinds of structures. So that's another interesting experiment around the same time. One of the experiments that's also very well known around the same time are the experiments of Klaus Sengstock, who had by then moved to Hamburg, and the thesis of Christoph Becker, who was generating these dark solitons together with a fair amount of radiation, sound waves, because he was imprinting them in the condensate, so he was creating sort of extra stuff, if you will. And these dark solitons were nicely propagating, were nicely oscillating through the cloud. And they could monitor that oscillation of the dark solitons. This very characteristic feature of the dark solitons could be monitored in these experiments. In fact, these experiments had an additional key thing. Remember I told you about multiple components? So they were able to put together for the first time a solitonic experiment involving two distinct hyperfine states, an F=1 and an F=2. And one of the two had a dark soliton. You see this thing with the atoms on the left, atoms on the right, and a density dip in the middle. And the other was filling the dip of the dark soliton. It was a bright soliton that was held together by the presence of this dark soliton. So the dark was like a potential that was holding together the bright. And indeed, those dark bright solitons were also oscillating in a nice way, in a systematic way, inside the trap. And they were observed for the first time, those oscillations, in these works in 2008. All right, and now let me pass to this analogy, because you see, many of these things in these areas are kind of known some 20 years earlier, have been done. There have been experiments in another area 20 years earlier that show very similar and interestingly parallel things. So this is an experiment from 1997. Remember I mentioned 2008 in the group of Moti Segev together with Zhigang Chen, in which they were taking two photorefractive crystals with two polarizations of light. So two species again, but now the species are light. They're not atoms. In a photorefractive crystal, so you shine the light and you measure what comes out at the other end of this nonlinear crystal. And so what they were doing is, one polarization was a dark polarization, the other polarization was a bright polarization of light. And they were doing three interestingly distinct experiments. In the first one, the intensity was low, so everything was nearly linear, and linear things disperse. Nonlinearity is not there to hold them together. So in the linear experiment, everything would disperse. They also did nonlinear experiments where the two species were decoupled. So the dark species, because it's self-defocusing, will form these dark solitons. But the bright species, you see, it has nothing to keep the soliton together. There are no bright solitons in self-defocusing media. So the thing would actually disperse over time. But then, when you put together the dark beam with the bright very robustly in these two polarizations of light, a dark bright soliton would be held together in this system. Okay? So that's an experiment which showed a single dark bright soliton, and then they got a bit cavalier and started using interesting names as well. They started having two solitons and started affectionately calling them solitonic gluons. So they were trying to do analogies with particle physics, you see. And so what they realized is the dark solitons, sorry about that, the dark solitons interact repulsively, so the two dark beams interact repulsively. If you have two bright beams and they are in antiphase, they interact attractively, so you balance the repulsion with the attraction to form solitonic molecules for the first time. So they were able to realize this in theory, and then they started playing with this in the experiment by having a fat dark beam coupled to two in antiphase bright beams, and again they did the triad of experiments. In linear evolution, everything disperses away. Nonlinearity is not there to help to hold it together. In nonlinear but uncoupled evolution, the dark solitons will be happy to stay, but the bright ones, there is nothing to hold them together, so they will still disperse. But when you put together both the coupling and the nonlinearity, you will form these solitonic molecules that we talked about, these things that they called solitonic gluons. So this is an interlude to tell you that in other areas, the same kind of physics has been developed under sort of a different setting, okay? So I think that's interesting. It's an interesting parallel to learn from. Okay, so this motivated further experiments in the atomic realm, in particular experiments by Peter Engels. This is around 2011 or so, and Peter sort of realized a dark bright soliton as well, and saw also this nice oscillation of a single dark bright soliton in a parabolic trap. So this is yet another experiment in which Peter was actually able to very nicely also trace the motion of the center of this dark bright soliton. Moreover, he was able to monoparametrically examine how this frequency of oscillation would change as a function of the mass of the bright soliton. And what he found, which is interesting, is that the soliton world is kind of like the real world in some sense. Allow me the analogy. In a sense, the fatter you are, the more bright atoms you have, the slower you move, the larger the frequency, the larger the period, the smaller the frequency. So it takes you more time to move if you have more mass, okay? So it's kind of like the real world, the soliton world is kind of similar in that sense. So that was with a single soliton, but he was also able to do experiments with two solitons kind of doing their soliton thing, going through each other in interactions of this sort. And in fact, then he kind of got also a little bit interested in this multi-soliton affair, so going maybe closer a little bit to turbulence. He started doing far more dramatic experiments. He took one condensate over here and one over there, and he kind of slammed them into each other. This is the so-called counterflow experiments. In these very dramatic counterflow events, occasionally he could see states, metastables now states, in which two dark solitons would trap two brights. States in which three dark solitons would trap three brights, and so on and so forth. So he could see that these solitonic states were integral features of the dynamics of the system. Okay, they would spontaneously merge in these systems, but these were too complicated to sort of hold these states together for long. Okay. All right, yet another experiment that is interesting from around the same time, 2013 or there around, the experiment that physicists dream of, so interaction of a wave with a barrier or a well. So here is an atomic barrier, a blue detuned laser beam that pushes atoms away, and here is a dark bright soliton. The dark bright soliton comes at the barrier, and it has enough energy, enough kinetic energy to overcome the barrier and pass to the other side. So this is a transmission experiment. On the other hand, if the blue detuned laser beam is too strong, if the barrier is too high, then the dark bright solitons are coming, but then they will get reflected. So they come, they hit, they get reflected. Okay? So these kinds of experiments have been done as well, although I think they need much more analysis than what has been already done. Here's another experiment of around the same time. Some of the experiments that Peter Engels did, he found a different kind of state. Not the one which was a dark bright soliton, the clear one that I showed you before, but a different state in which one of the components had the dark soliton here, and the other component had a complementary dark soliton. It's as if there were two dark solitons that were like paired. And the one that had the dark soliton here had the bright on the other side, and the one that had the dark soliton here had the complementary bright on the other side. So these were like a pair of dark bright solitons. These are called dark solitons and have very interesting dynamics because they actually breathe in a molecular kind of way around each other. So one can actually explain these through symmetries of the system, in particular SU2 rotations of the original kind of two-component system. But the main thing that I want to impress upon you is that not only can you have a dark coupled to a bright in the one component, not only can you have a dark coupled to the bright in the other component, but you can have these kind of dark states also as parts of the dynamics of the system. Okay? So the symmetries of the problem allow for it. All right? Then enter 2016, my first visit to Rouen, and Ionut was interested in doing a sort of good example for our numerical codes, and one of the examples that I proposed at the time was a different state, something called a dark anti-dark soliton. So contrary to what I've shown you up to now, let us now take two miscible species. So this is one atomic cloud, this is another atomic cloud, and one of them has a dark soliton that creates a potential again for the atoms of the other component. So the dark soliton creates a bump on top of a finite background. These kinds of bumps on top of a finite background are called anti-dark solitons. So this is an example from Peter Engels' lab of a dark anti-dark soliton. To tell the difference, here is a dark bright. You see the background of the bright is at 0. And here is a dark anti-dark. You see the background of the anti-dark is always finite. So this is kind of a different state. And in fact, it also oscillates in the trap, but with a very different frequency than the dark bright. So that's another kind of soliton in the zoo of solitons that I'm showing you. And then come 2018, experiments with spinors become more tractable in one dimension. So this is again Peter Engels' lab in 2018, realizing a 3-component spinor condensate. In these condensates, you can have dark solitons in 2 of the species and bright in the third. This is called a dark, bright soliton. Or you can have a dark soliton in one of the species and 2 brights in the other 2. So this is a dark, bright soliton. So there will be dark brights and dark, bright solitons in these 3-component kinds of condensates. And these have become more popular over time, and this is a work of Markus Oberthaler's group in 2020, just around the time of the pandemic, in which they were able to realize experimentally these dark, brights and check them against analytical expressions and show that if you actually have a phase jump somehow in this dark component, then you will generate dark, bright solitons. And if you don't have a phase jump, then the whole thing will disperse away. So here there is no generation of dark, brights because there is no phase jump in the dark soliton. But here where you have a phase jump, a pair of dark, bright solitons will emerge. And since you can generate a pair, here is a pair of dark, bright solitons. Here is another pair of dark, bright solitons. So you can slam them at each other. You can generate collisions, again, of these 3-component solitons. And here's an interesting thing that happens in these collisions. If you look at the density, the total density, it will look to you as if they are particles colliding. But if you look at something called the polarization, the 2 species, the +1 and -1, having the relative densities, what can happen is one of the species can have more atoms on the one side and the other species less atoms on the other side. That is, there can be a symmetry breaking event coming out of these collisions. This is an event that has been predicted in the theory of integrable systems as a function of the relative phase of these incoming solitons, and that feature has been observed in these experiments in the group of Markus Oberthaler in 2020. And just the very recent addition to the mix, Peter Engels has been able to do something that people also in optics are thinking quite a bit about, to generate states with many solitons sort of wound up together. So these are, you can see these are kind of dark, anti-dark, dark, anti-dark, dark, anti-dark. So this is an array of dark, anti-dark solitons and the corresponding theoretical simulation. And you can have many dark, bright solitons. So this is just one component that has dark, bright, and so on. Many of them wound together so that you can introduce interactions between them and collisions in this thing that we call a dense collisional complex of solitons. So basically, instead of having 1 soliton or 2 solitons, you can have whole gases of solitons. And in analogy to what people are doing in optics, by the way, people in optics are also doing such gases of solitons and observe their collisions and interactions in the way of turbulence, or starting to think about turbulence in these systems. So, okay, so that's kind of my overarching trajectory from 1999 till 2022 or therearound, a sequence of experiments to show you that this theme keeps getting new and new additions, keeps getting new and newer kind of features that are exciting to study from the experiments. All of what I showed you were really experiments. Now I want to turn a little bit to mathematical tools. What is it that we can understand out of these experiments? And so I will start very simple. I will start one-dimensional GPE with an external potential, and I will argue that there is 2 limits in which we can really understand things within this equation. The first limit is really what we call the linear limit. So it's the limit of very low density. Think of a density of size square root of epsilon, where epsilon is a small parameter. Then everything else is going to be order square root of epsilon, and this guy is going to be epsilon to the 3/2, so it's going to be negligible. If this guy is negligible, then we get a quantum harmonic oscillator. And quantum harmonic oscillators we know and love. We can really analyze them. So what we can do, even though it is not physically relevant at those low densities, the GPE is not a good model for condensates. Nevertheless, it's a place where mathematically we can do a lot of analysis. So we can say, let the wave function be a small thing times a linear eigenstate plus corrections, and let the chemical potential of these stationary states be the linear eigenstate plus small corrections. And then if you do something like this, then to leading order you will find the linear eigenproblem, and then you can do corrections to that, that is, you can solve for the next order, you can find from solvability conditions the next order eigenvalue and so on and so forth. That is, order by order, you can do perturbation theory and analyze those states. Okay? And not only can you analyze the existence of those states, but you can look at the linearization problem, the so-called Bogolyubov descent problem, order by order again. To leading order, you find the linear problem, a diagonal problem, and then nonlinearity comes in. But you can really study those problems order by order. Okay? And what do you find? Well, here I'm showing you the dark soliton, the first excited state of the quantum harmonic oscillator. At the linear limit, you start with the 3/2 omega. That's sort of the first excited state of the harmonic oscillator. If you put in a defocusing nonlinearity, then the number of atoms as a function of chemical potential moves like this, and you can predict it theoretically. If you put a focusing nonlinearity, the number of atoms as a function of chemical potential moves like that. This is sort of like a bifurcation diagram of this state, of this first excited state. So you can predict that. Not only that, but you can also predict the modes of linearization, the BDG modes of the system. You start at the linear limit and you go to the defocusing nonlinearity and you find that the eigenmodes of the system move in a particular way that you can predict analytically. And then you go all the way towards high chemical potentials, large chemical potentials, and that's another limit where you can do things analytically, as I'll show you in just a minute. That limit is the so-called Thomas Fermi limit, the large density limit. And why do I say it's important to be able to do this analysis? Because there are some topological features in this analysis. In particular, you find that this system that has a dark soliton has all the modes that the ground state has. The ground state is the state without the soliton. It has a dipolar mode, it has a quadrupolar mode. All these modes are present. But then there is one topological mode, a so-called negative energy mode, that is not present in the ground state. That's the lowest non-zero frequency. And if you actually excite that mode, what you will find is it is exactly the mode that Klaus Sankstock was observing in his experiments. It is a mode of vibration of the soliton inside the trap. And we can actually find something about the frequency of that vibration. Okay? So that's the interesting thing here. And let me sort of give you an example, first of all, of the perturbation theory, that is order by order you can find what the frequencies are. Like this frequency that I showed you over here, you can find that it is 1 minus epsilon square up to higher order corrections. But you can also find the opposite limit. This is the large density limit over there, the large chemical potential. And for that limit, you can find all the frequencies of the ground state. Here are the frequencies of the ground state, the dipolar, the quadrupolar, the higher ones as well. Sandro Stringari had predicted those as early as 1996. But you find that there is one frequency that pertains to the soliton, and that frequency, which is 1 over square root of 2 of the frequency of the trap, is the frequency of this motion that Klaus Sankstock was observing. Okay? So let's kind of go to that limit of large density, and try to understand that one mathematically as well. Okay, so what do? Before we did perturbation theory, now I'm going to the opposite limit, to the highly nonlinear limit. I know for the highly nonlinear system that it is a system that is Hamiltonian, that it has an energy. And I know that it has a dark soliton. This is the integrable theory coming in, telling me that there is an exact soliton solution that is parametrized by the position of the soliton center and the soliton velocity. So I can take this expression and calculate the corresponding energy. And if you do that, you'll find that the energy of this dark soliton depends on the chemical potential, on the density, and the velocity of the soliton. That's all that it changes, that it depends on. And then Konotop and Pitaevsky 20 years ago come and say the following thing. Okay, let me put the soliton in a trap. What changes? What changes if you put the soliton in the trap is that the density, instead of being mu, instead of being equal to the chemical potential, it is close to the center of the trap, mu minus v of x. It is slightly lower. So they said, well, the energy should still be an adiabatic invariant of the system. So wherever I see mu in this expression, I should substitute mu minus b. And if you think that now the energy is an adiabatic invariant, you multiply this expression by 3/4, raise it to the 2/3 to realize that the parenthesis should be a constant. And if you take ddt of that constant and set it to 0, you extract an equation of motion for the soliton inside the trap. And what does this equation of motion predict? It predicts that if you have a parabolic potential, the soliton should oscillate with a definitive frequency. Exactly the frequency that we saw 2 slides ago, the frequency 1 over square root of 2 of the frequency of the trap. That's all that it could do. Okay? And that's what the theory exactly predicts. In fact, it predicts the motion for any potential that you can possibly give me. All right? So it's a nice theory. And that's all for one dimension. But remember the solitons I showed you? They were not one-dimensional in Klaus Sengstock's or Bill Phillips' experiments, the very first experiments. They were higher dimensional. In fact, what Carlos showed us in the morning also had these line solitons breaking up in vortices. So how do we understand that? Well, here's a line soliton, and indeed it breaks into vortices. If you let it go, here it is, that dark soliton, it sort of has a phase jump. That dark soliton starts bending and eventually breaking into vortex-antivortex pairs. That's exactly what those experiments showed as well. And so how do we understand this feature? Okay? So let's try that. Before I show you that, here is a variation, here's an undulation with a higher wave number. It will actually break the soliton and it will create 4 vortices instead of 2. Okay, so that is another realization of this experiment. So how do we put our hands through this? How do we understand it? Well, in this case, we have a 2-dimensional GPE. And so we have a line soliton, what I call a filament. But you see in the filament, it's as if we have a single dark soliton for every y. And for every different y, the center is at a different position. So if I think of the soliton as having a center, xi, that is a function of y, I can actually extract not an OD for the position of the center, but a PD, because the center now depends on which y you are at. So let me try that. Let me substitute the same soliton in. I do exactly the same calculation for the 1D terms, and now I have a y dependence of that center, so I can calculate that y dependence in that integral of the energy as well. And now I take this energy and find its derivative with respect to time to be equal to 0, and out of this time derivative being equal to 0 comes not an OD, because I'm in 2 dimensions now, but rather a PD for the position of the center as a function of y and t. How does this filament move over time? You see, when I showed you these pictures, I was actually including a green line. The green line is the prediction of this filament PD for how the soliton moves, the soliton having a different center position at each y, how this filament moves over time before it breaks. Okay, so that PD does very well in describing this filament, and in fact has a number of interesting features. In the case where we have no y dependence, it falls back into Konotop-Pitaevsky, just as it should. In the case where there is no potential, it falls back into something that was known 35 years ago about transverse solitons becoming unstable. So it has both of these interesting features. But in addition, it allows you to find that filament equilibrium and to linearize around it to find all the modes of potential instability. And here's how well it can capture these modes. Here's a mode where the green and red is the numerical prediction, the blue and magenta is the prediction of this theory, and this is how well one tracks the other. And as you go to large chemical potentials, all the modes of instability of the system are captured by this filament theory. So this is a theory that allows you to characterize the dynamics of this system. And by the way, I told you about interactions of solitons. So let me now try interactions. So let me try 2 solitons, one at x naught and one at minus x naught, 2 filament solitons. Then each one will have its own energy, but additionally the solitons are interacting. So this interaction is a repulsive interaction that you can write down explicitly. Okay? So if you put together both the individual solitons and the interaction, you get a PD for their position of the centers, which covers each one of the solitons by itself and the repulsive interaction between them. So what you can capture with this is the equilibrium position, because now the solitons are pushed away by each other, but the trap brings them back. So they have an equilibrium, and also all the modes of linearization. So here's a mode that becomes unstable. The orange and red is the theory. The blue and magenta is the numerical computation. You see how well one tracks the other. So you can actually capture the linearization around these solitons as well. And let me show you this to convince you how well this theory can do. Here are the two solitons, right? And they are interacting. Each one will become unstable, but they will affect each other, okay? As they affect each other, they start bending. And the green theory, the filament theory, is capturing that bending. And as they approach each other, the bending is still captured by the filament theory, and they will become unstable due to undulations. And even past the point that they break, still the filament theory captures something kind of accurate about how the solitons are evolving over time. And here's an example of a higher wave number, and you see how the filament theory, the green, is capturing the undulation, the interaction of these soliton filaments over time, okay? And when you have more, you can create more exotic effects, effects that kind of even look like, or sort of, if you remember Carlos' corresponding slide, start having the feel of some sort of turbulence, because now as they exchange, as they sort of interact with each other, they break into a whole zoo of potential vortices. They break into something that has the feel, although it needs to be further examined, of this kind of turbulent dynamics. And then with more filaments, you can have more of that, and so on and so forth. And these are motivated by experiments that Brian Anderson has done relatively recently that have motivated this study. And not only can you do this for straight filaments, but because we talked about vortex rings, and many will talk about vortex rings, you can also do them about radial filaments, okay? So there is something called a ring dark soliton, and the main thing that changes for a ring dark soliton is that you have the element of curvature, but you can still calculate the energy. And you also know that a ring dark soliton will have undulations along the azimuthal direction, and you can account for the undulations along the azimuthal direction. The rest of it looks like one dimension, but here's curvature and here's azimuthal undulations. You can take this into the energy, extract the equation of motion of a radial filament, and then you can find that, first of all, the radial filament has equilibria because curvature pushes the ring out. The trap pushes the ring in. So the two balance and give you an equilibrium filament. Moreover, you can find the modes of vibration of that equilibrium filament, and here's how beautifully simple they become for a case of a parabolic trap. And you realize that many of these modes, as n becomes large, n is an integer, they are unstable, and here's how well those unstable modes of a ring are captured, and here's how well those unstable modes allow you to track. Again, the green is the radial filament, the ring dark soliton, allow you to sort of find that the soliton should undulate and should eventually break into these arrays of vortex-anti-vortex pairs. So you can actually describe solitons and filaments not only in 1D, but in 2D. Not only in the case of straight solitons, but also in the case of radial solitons. You can still capture their dynamics as well as this. Okay, and here's another undulation, a higher wave number, a higher n, and you can still see how the filament method, the green curve, captures the effective dynamics, the growing, the unstable dynamics of this ring filament. Okay? And by the way, remember I told you the original pictures were three-dimensional, right? And so you can play the same game in 3D. That is, you can say the center of the soliton depends on the y position and the z position in 3 dimensions. So you can play the same game for a planar dark soliton. Or you can play the same game for a spherical dark soliton, in which case you vary along the two spherical harmonic kind of angles. And you can derive equations of motion for the evolution of these solitons and find an equilibrium between curvature and the parabolic trap. And you can find the modes of linearization around these solitons and capture them in the case of a parabolic trap. Here is one of these spherical solitons. You cut them along the x, y, and you see a ring. You cut them along the y, z, and you see a ring. It's a spherical soliton. And here are the modes of instability and how well the black lines, the predictions of the theory, kind of capture these kinds of states. And in fact, motivating the vortex rings, if you take such a ring, such a spherical soliton and evolve it in time, it will become unstable and produce multiple vortex rings, a state that we affectionately like to call a vortex ring cage. Okay? So that's kind of motivating how vortex rings spontaneously emerge through the understanding of this theory. And then, as I said, there are all these kinds of multi-component generalizations. So let me tell you a word about those. Remember that a generalization of a dark soliton is a dark-bright soliton, is a two-component state. That, from integrable theory, is still analytically available. Here is an exact solution of the integrable two-component model. It's a dark soliton in one of the components and a bright soliton in the other. It has a position of a center, a speed, a width, and a number of atoms in the second component, parametrizing this complicated dark-bright soliton solution. But all of what I told you can still be done. That is, you can find the energy of a dark and the energy contribution of the bright component. This is the number of the atoms in the bright component. So you can find the energy of a dark-bright soliton. And then when you put a second dimension, you can find the contribution of the second dimension to this energy. And then when you find the linearization frequency, and this is what I want to show you, remember the omega over square root of 2? It's still there. It's what the dark soliton contributes. Remember that Peter Engels was finding that the frequency was decreasing for fatter solitons. It is this contribution over here. Remember how in 2 dimensions the dark soliton became unstable? It is because of this term. And in 2 dimensions the bright soliton also contributes. So every term that you get from the theory has a correspondence to the physical phenomenology that you expect to have. Okay, so this analysis gives you explicit mathematical expressions. It allows you to put your teeth into the instabilities and the dynamics of these systems if you understand how to do this kind of analysis. Okay, so that's kind of what I was hoping to show you, and this analysis matches very well with the numerics. And here is an example of this dynamics. The dark, bright soliton line, you can see that it starts bending and starts breaking, and when it breaks in vortices in this component, coupled to bright solitons in the other component. So it presents new states in its own right. Vortex, bright soliton pair. So it motivates us to study yet other kinds of solitary wave structures, like the vortex brights. Okay? And by the way, these vortex bright solitons were found already in 2001, just people didn't discuss them. With Lorette, in fact, we had the papers discussing these kinds of structures, but they were found as early as 2001 in experiments by Brian Anderson. Here's the vortex component, but it was filled by a bright soliton component in the other condensate, in the other component of the condensate. And by the way, remember I talked about these planar dark solitons and the linear theory. If you do linear theory of these planar dark solitons, you can find that they become unstable. And when they become unstable with a bifurcation, which is a symmetry breaking bifurcation, what do they produce? They produce rings. So the rings are not disconnected. They are exactly the kind of state that emerges from this instability. So you see, if you are able to do this theory, linear theory or highly nonlinear theory, it gives you motivation to understand either new states like these vortex brights or states that have been already observed in experiment like these vortex rings. So the green is a ring of vorticity, the red is the corresponding density that is a vortex ring that emerges from this bifurcation. So it's something that if you cut it along this direction, you see a ring along the XY, but if you cut it along the YZ, you see something that is like a vortex-anti-vortex pair. So you can understand these kinds of states as well, and of course generalizations of these states. And by the way, a filament theory is possible even for vortex rings if you account for the kinetic energy, and the cylindrical arc length gives you something about the potential energy, so you can understand something about how the ring evolves in the azimuthal direction in time, and how the ring evolves along the vertical direction and along the azimuthal direction, so z along theta and also time. And if you analyze these equations, again analytically, fully, and so on, you can find something that was actually known from a long time ago, that is, vortex rings are very particular creatures. As a function of the anisotropy of the system, they are stable or quite unstable. If the system is prolate, they are unstable. In particular, if the ratio of the trap along the Z over the trap along the R is less than 1, a prolate condensate, they are unstable. That's the red. If they are very oblate, if they are very sort of crushed, for trap strengths lambda larger than 2, then they are also unstable. But then there is a sweet spot which is not prolate, not too oblate, just the right oblateness of the condensate, such that the vortex rings are actually robust. So this theory kind of tells you where should you look for stable vortex rings, and it tells you that analytically. Okay, so that's kind of the beauty of these theories. Here is an unstable example of a vortex ring. In this particular case, you can see it breaks into 2 vortex filaments, but there are also stable guys. And in the place where the vortex rings are stable, we actually looked quite intensely to try to find knots. We know that lots of other people in the room have sort of thought about knots, and we found even knots that were very long-lived, survived for very, very long times, but never did we find a truly stable torus knot, and so those states are probably unstable generically. Let me skip this and sort of finish by telling you something about, first of all, these sort of vortex bright solitons that I told you are also a possible state in the system, and we can actually find them motivated by the experiments, the numerical experiments that we did before, and therefore, let me just skip, I think, all this and maybe go, oops, I'm going in the wrong direction. So let me just go forward towards the end. Let me just say that too far down. So there are also states like the vortex bright in 3 dimensions. So here's a vortex line together with a bright soliton. Here's a vortex ring together with a bright soliton. So the generalization of the 2-dimensional states in 3D are also possible. And let me just show you a few movies to end the whole story. So I have them in a separate presentation. Just give me 1 second to load it up. I wanted to show you a couple of these things in action and how well the theory does in them. If this cooperates, there we go. Okay, so this is the ring dark soliton that I talked about, and the corresponding theory is actually in green. So here's how the theory kind of evolves over time. You can see the thing becomes unstable, it grows, but it also starts ondulating, and you can follow that ondulation over time until the thing breaks into vortex-anti-vortex pairs. So this is an example of an instability that you can capture with this method. This is an example of a sort of pass to Ricardo, who will talk about vortices and what we've done with vortices later on, next week, actually, early next week. So our friend David Hall, I like to think, has like has something like a, sorry about that. Oh, that crashed. Okay, so it probably doesn't, okay, let's see. Doesn't want you to see that movie, I think. Okay, so let me do one more try, and if I fail, I will just quit. Here. Okay. All right, so this one, come on. There we go. Come on. There we go. So our friend David Hall can actually put together either 3 vortices or 4 vortices. Okay. Yeah, I did. I thought I did. Okay, so well, I think it just crashed twice. I'll go straight to the movie. Okay, so let me try one more time. Okay, so let Ricardo show the movie. Let me just summarize what you saw, and I'll coordinate with Ricardo so that he tells you about the movie. Let me just tell you what I just told you, okay? So basically what I told you is that in these systems there has been a lot of experiments over some 25 years showcasing structures, interesting interactions between the structures, generalizations of these structures in higher dimensions, instabilities of the structures, all of these things. And these experiments have prompted theory that kind of goes along with them. The theory goes from linear limits, where we can really understand things based on perturbation theory, to highly nonlinear limits, where these kinds of filament-type approaches, these kinds of highly nonlinear approaches are kind of game. With everything in between sort of feeding from analytical solutions, from integrability, from nonlinear theory, and so on and so forth. We can really understand many things about these solutions. That being said, there is a lot that is still unclear. What happens if we sort of put together lattices of these vortex rings? What happens if we put together integrable arrays of these solitons and sort of lead them to turbulence? All these kinds of things and many others are kind of still unknown, in terms of the dynamics and in terms of these effective descriptions and how well they can capture the dynamics. So if any of you have any thoughts or interests or ideas about any of that, I would be delighted to talk to you about all that. And with that, thank you very much for your attention. Thank you.
So thank you very much, Panos, for this highly nonlinear, bright presentation.
Okay, thank you.
So there are questions.
Yeah, thank you. I don't know much about the solitons. So if, for example, in this quasi-one-dimensional, two-dimensional case, is there some sort of shear between the left and right part of the soliton that generates these vortices, or?
No, it's more like a nonlinear instability that generates the vortice. So the vortices, due to curvature, start sort of bending, and eventually when they bend, they will start sort of creating rotation, and this rotation will break them into vortex-antivortex pairs. So the solitons themselves have no vorticity. The vortices, as Carlos said, sort of come into integer sort of pairs, so you have to have a conservation of vorticity, so you generate one vortex and one antivortex out of each one of these solitons. And if multiple solitons interact, or if you have sort of rings and so on, then you can generate more than two. You can generate 4 or 6 or 8, many solitons, as in some of the interactions that I showed, especially the interactions of multiple line solitons, like the ones that were right about, give me a second, here. So here, there are multiple line solitons coming together. They start bending each other. You see, this is going to be a prime spot for generating 4 vortices. And indeed, here are 4 vortices that are coming together, a pair coming out of each dark soliton, and so on and so forth. And as they are more complicated, there are kind of more symmetry-breaking events. And there is kind of plus, minus, plus, minus, plus, minus. The whole thing breaks into many vortices. Yeah, it is a nonlinear instability in the system, but of a different kind of structure. So yes, parallel, but not the same.
Hi, Panos. Thanks. Fantastic talk. 2 questions. The first one, following on from this one, is can your model predict when it will go unstable?
If you give, okay, let me think about that. So you can predict that it can predict the rate with which it goes. In fact, it is unstable. What this prediction says is that it's unstable from the very beginning. That is, the structure itself is unstable. And what it gives you is the rate of growth of that instability. So this instability will exponentially grow over time. What it will not predict, because that's not part of the theory, is when it will exactly break into, when the tension is such that it breaks it into vortices. That it cannot predict because the vortices are not part of the filament theory. They are kind of a separate entity where the soliton has now broken in different entities. But the instability and the capturing of that instability over time is part of the theory.
But in terms of curvature, you cannot predict it. In terms
not,
of the curvature.
not with this. You would need something that tells you that if the curvature is beyond the critical curvature, then the soliton cannot hold this together for that chemical potential and break. Studying that is interesting in its own right, but the theory itself doesn't give you that. The theory is a theory about a filament that sort of grows or becomes more curved over time. So that's an interesting question.
Thank you, and that leads to the second point. Obviously, this is fantastic, all within the Gross-Pitevsky, but there's a critical part that is played by quadratic trap, because what happens is while it's moving, there is sound emission, which actually is not in your theory.
Yes.
And it's only in a quadratic trap that this sound emission will act constructively to make sure these features stay in place.
That's absolutely right. So we have not incorporated, in what I showed you, we haven't incorporated the sound emission and reabsorption, importantly, which you know well and you've studied as well, somehow in the trap. In 1D solitons, we have done that, which makes me confident that we can also do it within this theory. You just need to sort of have a separate piece of these sounds, because in what I did, I was really having one structure in play, and this structure was, say, 1 or 2 or multiple dark solitons, but I need a separate term that includes these kinds of sound dynamics and involves something about the amplitude of these sound dynamics and so on, and that's an additional term that needs to go into the answer. So that's a very good pass or motivation to look into that, and I know we've done it with Dmitry Pelinovsky in 1D settings, where we have incorporated the effect of the sound, but we haven't done it in this filament, so thanks for that suggestion. Very good point.
Okay. So for the 1D soliton theory, you have this near linear limit, and then you have a fully Thomas-Fermi limit.
Yes.
So isn't there a way to like
bridge the two?
to go from linear to fully nonlinear.
That's an excellent point, and thank you for asking that. So the way that I like to think, and I know people like Stathis kind of know I've been always saying that, is these two limits have some simplifying factor, either low density or low inverse chemical potential. So there is some small parameter in which you can do theory. The in-between does not really have a small parameter to do perturbation in, or does not have a good starting point to do in. So my usual saying is, this you can analyze theoretically, this you can analyze theoretically, and then you bridge the two with numerics. Okay, so numerics is sort of the the grand equalizer. It allows you to go from one to the other, but these two limits, linear and highly nonlinear analysis, can lead the way. Okay, thanks for asking that.
Yeah, real interesting. I noticed that for your reduced model, the green line always stopped before seeing roll-up.
Okay.
So I wonder if
Let me see if you have an example. Like, okay.
Yeah.
So which one?
Further to the right.
Okay.
So there. And then
Yes. So this is
like
where.
to generate a vortex, you need kind of it to become
Yes.
multi-valued.
Yeah, but it cannot. By its nature, somehow, it has to stay aligned because you are really monitoring something which is xi as a function of y and t, so it cannot do it. You have to have something that allows you to detach the line and break it into filaments, into smaller filaments, which at the moment does not exist in the theory. So you need something that allows you to decouple once this thing maybe becomes too steep. That tells you you need to now break this into two separate filaments and so on. At the moment, this doesn't exist in the theory, but if you or anyone has any idea about how to do this systematically, we would be delighted to hear about it. That's a very good observation.
Thanks.
Okay, thanks.
Other questions? No? So thank you again, Panos.
Okay, thank you.